start. We have main engine start. 4, 3, 2, 1, 0, and liftoff. The liftoff of the space.
In our natural pursuit of knowledge, space has always mystified and beguiled us. Over the past 5 decades, we've pushed the final frontier inevitably onward into the ether. The cost has been colossal. Now every day, new data, new conclusions, and the thirst for deeper exploration propel us inexorably onward. The advantages of the discoveries made through space travel are myriad, but the fundamental curiosity as to what is out there will always fascinate and taunt us. Come with us now into the unknown and discover the disappearing frontier. In this edition, the Hubble telescope, providing astronomers with a clear window to space, rewriting the textbooks on how we view our universe. NASA has sent many shuttles into space, but this one was dedicated entirely to life science research. And to help in their research, they took along what else? Jellyfish. Sedimentation and buoyancy-driven convection are dominant on Earth. They can mask or hide the true behavior of other transport mechanisms that fluid physicists are trying to better understand. And stars take on a new dimension. You'll see incredible pictures of far-off planets and have the electromagnetic spectrum explained in this story entitled A Symphony of Light. In 1990, Shuttle Discovery launched Hubble's Space Telescope, the most powerful observatory ever built. Able to image detail up to 15 billion miles away, Hubble has provided astronomers with a clear window to our universe. Soon after Hubble was deployed, scientists discovered an aberration in the 94-inch primary mirror. Even so, the huge spaceborne telescope has been returning a steady stream of new information, particularly with the aid of computer enhancement. Similar processing has been used on data from other spacecraft, like Voyager, which traveled past the planets. Enhancement now brings out more detail for Hubble scientists. This is the telescope's original image of a galaxy 52 million light-years from Earth, as it's cleaned up to its final version. Here, light pulses in a straight line between Earth and a distant quasar. Years ago, Albert Einstein suggested that if a uniform object crossed the path, light would bend into a ring, but if the object were not uniform, the ring would break up into 4 patches. Known as the Einstein cross, Hubble reconfirmed this part of Einstein's theory of relativity. Hubble also showed scientists a celestial X marking the exact spot of a black hole with the possible mass of 1 million of our suns. Astronauts were already training to fix the Hubble mirror problem in late 1993. By substituting a special component in the telescope, the aberration was repaired. Called CoStar, this corrective optics package contains a series of mirrors that work like contact lenses to restore Hubble close to its full imaging potential. In a clean room at NASA's Goddard Space Flight Center, technicians also practice removing the spacecraft's star tracker, which helps point the telescope. In the meantime, Hubble continues to send back fine detail of the planets, faraway galaxies, black holes, and distant stars, rewriting the textbooks on how we view the universe. The compelling sight of a launch that takes the shuttle into the mystery of space. The astronauts on STS-40 were making history as their payload consisted of microorganisms. These microorganisms, or jellyfish, were sent up by NASA to help learn more about living in space. Although it looks easy floating around, living in space certainly has its problems. In the early days of space travel, there was so much we didn't know. Before humans traveled into space, animals were sent while scientists checked their responses. When the first animal space travelers returned to Earth, they brought back enough information to safely send the astronauts into space. But even when NASA sent John Glenn into space to orbit the Earth in 1962, they still didn't know exactly how his body would react. Of course, as more astronauts were sent up, the scientists learned more about space travel in relation to life sciences. Life sciences are the study of living things, how they grow, function, and interact. There had to be more research done in space. On Earth, we feel the effects of gravity almost everywhere, but you can experience a similar environment to microgravity by going underwater. Fortunately, you can't stay underwater for long periods of time. You can experience microgravity on a roller coaster ride like this, or train in NASA's special aircraft, the KC-135 that flies up and down. But the problem is that simulated microgravity only lasts 15 to 20 seconds. In space, microgravity lasts for as long as you're in orbit. It becomes hard to tell if up is up and down is really down, so it's hard to predict how body functions will react. That's why scientists conduct experiments to learn more about microgravity. Dr. Dorothy Spangenberg is the expert that made these experiments happen. She'd been studying jellyfish and had noted the similarities to humans. Dr. Spangenberg and her students had worked with jellyfish for years before the opportunity of sending them into space presented itself. Her research started nearly 3 decades ago by collecting specimens along the Texas coast. People from around the world heard about her work and sent her different specimens to study. The more she learned about jellyfish, the more she knew NASA could learn a lot from them. This is the Monterey Aquarium in California, where another team of researchers is learning more about jellyfish every day. Jellyfish are among the simplest organisms, but they have neurons or nerve cells similar to humans. They have sensors called gravity receptors located in their arms. These help them maintain their balance and know where they're going, like a built-in compass. The gravity receptors tell them that up is up and down is down. Humans have this too. To help us maintain our balance, there are gravity receptors located in our inner ear. After riding on an amusement park ride, you feel like you're going to fall down. That's because the motion affects your inner ear. Even after you stop, the fluids in your inner ear keep moving. This effect makes you dizzy. This type of motion sickness affects astronauts in space as well. By learning more about the development and function of gravity receptors, scientists hope to fight the effects of space sickness. By sending jellyfish up into space, they wanted to find out if they would react differently in microgravity. Would they still know what is up and what is down? There are more ways that jellyfish can teach us about living in space. Astronauts returning from space also suffer from calcium deficiency. We need calcium, of course, to keep our bones strong. Extended calcium deficiency causes osteoporosis, bone disease, and many gum diseases as well. Each jellyfish gravity receptor has a sac of calcium sulfate crystals, just as our inner ear has calcium-containing crystals. Jellyfish were used in this experiment not only because of the similarities to humans, but because of their small size. NASA needed a small animal that they could study as it developed in space. More than 100 jellyfish polyps can fit on a dime. The jellyfish are also easy to study as they developed in distinct individual phases. And its gestation period is only 6 to 8 days. When we travel in space, we have to take our environment with us. We need oxygen and food and the things that protect us from the elements of space. Jellyfish travel in space, they have to take their environment with them as well. Jellyfish on board SLS-1 were placed in specially prepared bags filled with salt water and carried in an incubator to stabilize their environment. Just before they launched, Dr. Spangenberg and her students poured an iodine solution into some of the bags to encourage the jellyfish's development. By the time SLS-1 settled into orbit, the jellyfish had passed their first test, proving that a microorganism can withstand the forces of liftoff. To help the jellyfish polyps develop into Aphyra, the first stage of development, the iodine mixture was added to another group of jellyfish. While experiments were conducted on the orbiter, simultaneous experiments were conducted on the ground. The Earth research is called the control, an experiment that doesn't have the variable whilst being tested. Every experiment should have a control as it gives something to compare the results against. Both groups of jellyfish were videotaped as they swam in the hope of recording any changes in their movement or behavior. One of the most exciting changes happened almost straight away. Remember how the jellyfish use their arms to pulse up and float down to feed on Earth? In microgravity, the jellyfish moved in circles, but they were still able to pulse and swim easily. In fact, despite being in a microgravity environment, the jellyfish polyps developed normally. After 9 days in orbit, they began to prepare the jellyfish for the trip home. One group was secured in the locker to be immediately studied after landing. The second group was preserved in a special liquid to be studied and compared to the jellyfish used in the simultaneous Earth experiments. Dr. Spangenberg spent more than a year studying the microgravity jellyfish and comparing them to the Earthbound group. The results surprised everyone. After swimming in circles in space, some of the jellyfish swam a little differently on Earth. However, most of them adapted to their normal behavior patterns pretty quickly. Scientists believe that their gravity receptors behave differently, which made them more sensitive to microgravity. It was discovered that the development from polyp to Aphyra was unhindered in space, and they found most of the jellyfish to be completely normal. The experiments will result in more knowledge about human cells, the basic unit of life, and how they develop. The more we can learn about the human body and its responses on Earth and in space, the more we can control diseases and how the body responds to different environments. Fluids are any gases or liquids that will flow and assume the shape of their container. From the silicon chips that drive our high-tech society to important medical research crystals grown from solution to the combustion process that is so important to our society. Fluids in one form or another affect us all. An example of sedimentation is what happens when fluids of unequal densities are combined. Gravity causes the fluids to settle in layers, with the heaviest, more dense fluids forming on the bottom and the lighter, less dense fluid forming on top. The other phenomenon, buoyancy-driven convection, can occur when the temperature of the fluid changes, causing changes in its density. For example, when heat is placed under a beaker of water, the water at the bottom expands as it gets warmer, becoming less dense. Gravity then pulls the cooler, denser water at the top to the bottom, where the cycle is repeated. Diffusion occurs because atoms in a highly concentrated region naturally tend to move to areas of lower concentration. When the small container of coloured water is placed into a large container of plain water, the coloured water begins to move or diffuse to less concentrated areas until the two liquids are evenly distributed. Every liquid has surface tension, the result of the force that attracts liquid molecules to each other. The surface tension of water is great enough that a needle can float on the surface. Surface tension can change. By adding a surfactant, in this case a drop of soap, surface tension of the water changes enough that it will no longer support the needle. Another way to change surface tension is by changing the temperature of the liquid. Watch how the oil in this pan changes to the effect of temperature. These movements are called surface-driven flows. Capillarity can be described as the attraction a fluid has for itself versus the attraction it has for a solid surface. When a small diameter capillarity tube is placed in coloured water, we can see the water rise high into the tube. Do the same thing with a different liquid and it won't rise as high. That's because the capillary forces are different in each case. Unfortunately for scientists and others that work with fluids, sedimentation and buoyancy-driven convection dominate experiments involving fluids of different densities, and experiments where temperature differences are involved. And because sedimentation and buoyancy-driven convection are dominant on Earth, they can mask or hide the true behavior of other transport mechanisms that fluid physicists are trying to better understand. Microgravity is ideal for experimentation, as its low gravity virtually eliminates sedimentation and buoyancy-driven convection. Throughout history, man has looked to the stars and pondered its mysteries. These amazing objects are so far away that we, or even robot spacecraft, can't go and study them directly. The only way we can learn about them is by studying the radiation they emit and send to us at the speed of light across huge distances. That radiation consists of visible light that we can see through telescopes, but also invisible radiation, most of which doesn't even penetrate the Earth's atmosphere. The more successful we are at decoding the radiation messages, the more we can expand our knowledge of the universe. Since we learn about space by studying the radiation that comes from these objects, let us have a look at the electromagnetic spectrum and discover its mysteries as we explore the universe and its symphony of light. As light is made up of different colors, a telescope with a spectrometer can do the same thing with starlight that a prism does with sunlight. Each star has a unique color pattern. These color patterns are chemical signatures. Like fingerprints, they help identify the star. By looking at the detail of the color patterns or spectra, you can determine the temperature, pressure, and the chemical elements in the star. Every element has its own distinctive color. For example, neon here gives off its very characteristic red color. In this tube is hydrogen. It gives off its purple or violet light. These colors are at the opposite ends of the visible spectrum. For centuries, visible light was our only source of information about our universe. Then early in the 20th century, astronomers discovered radio waves coming from outer space. Even though bigger and more powerful optical telescopes were built, they were still limited in the information they could gather. The job of space mission STS-35 was to rocket above the atmosphere and operate the Astro-1 observatory. This was NASA's first mission devoted entirely to astrophysics, science that investigates the size, mass, temperature, and chemistry of celestial objects like stars and galaxies. Studying celestial objects from observatories on the ground is like listening to music with the high and low notes filtered out. Radiation is generated by waves of energy rippling from a source, just like ocean waves. Light waves have high points or crests and low points or troughs. distance from crest to crest is the wavelength, and different frequencies result in different wavelengths. Traveling at the speed of light, radiation vibrates in electromagnetic waves. The electromagnetic spectrum classifies these waves by using their wavelengths and frequencies. Although the spectrum is continuous, it has been divided into 7 categories for easier identification. One end of the electromagnetic spectrum, radio and microwaves, are used for cooking, communication links, and for radar. Radio waves are used for communication, usually in the form of radio and television broadcasts. Although infrared rays can't be seen, you can feel them as heat from the sun or a heat lamp. In the visible spectrum, the color of light depends upon its wavelength. At one end, red light has a long wavelength and less energy, while on the other end, violet waves are shorter and are the most energetic of all types of visible light. On the higher energy side of the visible spectrum are ultraviolet rays. To most people, ultraviolet rays are the ones that tan or burn their skin. This happens because, although most of the sun's energy is in visible light, our sun is hot enough to emit some ultraviolet light, a small fraction of which reaches us on the ground. To astronomers, ultra-radiation tells about hot young stars that have just been born or hot old stars near their deaths. X-ray photons are even more energetic. When an X-ray picture is taken of your body, the bones absorb the rays while the soft tissue like your skin doesn't. This kind of picture provides your doctor with important information. Gamma rays have the highest energy and the shortest wavelengths of all. Certain radioactive material emits gamma rays. These rays are used in some forms of medical treatments, however too much exposure will cause severe illness. The Astronaut Observatory used 4 telescopes to gather different types of information at the same time on the same objects. It was the first observatory that could simultaneously take ultraviolet pictures of objects, study their ultraviolet and X-ray spectra, and determine their brightness and structure. The Astronaut Observatory has allowed scientists to view the universe in its entire energy range, and thus open a great window to the universe. But this is only a beginning to understanding the universe and its symphony of light.